There's a wave coming. It's taller than a 40-story building. It's moving faster than a commercial jet. And in the next few minutes, it's going to erase an entire coastline on a planet that, according to a lot of what you probably learned in school, never had a coastline to begin with. This is Mars, roughly 3.5 billion years ago. A chunk of rock the size of a small mountain just punched into an ocean hundreds of miles away, and the wave it kicked up is coming to collect. Here's the part that should stop you cold. For most of the last 50 years, the scientific consensus was that nothing like this could have happened. No ocean, no coastline, no wave. That consensus is dead. And the evidence that killed it is stranger than almost anyone expected. A lander that spent 4 years listening to the planet's heartbeat. A 6-wheeled Chinese rover reading an ancient seafloor like a crime scene. Rock layers scanned for hidden rhythms from 100 million miles away. Put it together, and modern science has rebuilt a Mars that carried oceans for the better part of 1 billion years, dragged sideways as the whole planet tipped over, blasted apart again by asteroids, brewed into something closer to dissolved baking soda than seawater, possibly stirred by a moon that doesn't exist anymore, and, this is the part that should really get you, maybe never fully gone at all. By the end of this video, you'll know exactly how scientists pieced that story together, and where a huge piece of that ocean might still be hiding, right now, under the ground. Let's start with the problem that almost got this whole idea thrown out. In 1976, NASA's Viking orbiters sent back the first real photographs of Mars, and geologists noticed something odd: terraces and low cliffs in the northern lowlands that looked like an old coastline. In 1987, physicist John Brandenburg gave the idea a name: Oceanus Borealis, the Northern Ocean. It was a thrilling idea, with a problem that almost killed it. Water always finds its level. On Earth, a coastline traces one smooth line around the planet, because gravity and rotation force it to. So a real Martian ocean should leave a shoreline just as level, a bathtub ring circling the globe. It isn't. Map the Martian shoreline, and it climbs and dips by miles over its length, kilometers higher in some stretches than others. To a lot of scientists through the 1990s, that wasn't evidence of an ocean. It was evidence people were misreading some other, far more boring process. The fix came in 2007, and one of the more elegant pieces of detective work in planetary science. Geophysicists Taylor Perrin, Michael Manga, and Jerry Mitravisa figured out the shoreline wasn't lying to us. Mars was tipping. It's called true polar wander. When a planet's mass gets so lopsided, the entire solid body reorients around its spin axis to stay balanced, like an unevenly loaded washing machine rocking itself into a new position. On Mars, the culprit is Tharsis, a volcanic bulge some 5,000 kilometers across, home to Olympus Mons, the solar system's largest volcano. As Tharsis piled up mass, it dragged the entire crest with it, warping every feature that used to be level, including a shoreline that really had been flat, billions of years earlier. Sit with that for a second. An ocean old enough to watch its own planet tip sideways underneath it. That story got one more twist. Later measurements show Tharsis actually formed near the equator, not far from it as the original fix assumed, which should have broken the whole explanation. Instead, in 2018, geophysicist Robert Citrin, working with Manga, proposed the real fix. The shorelines in Tharsis weren't sequential. They were simultaneous. Citrin's team compared two shorelines, an older one, Arabia, and a younger one, Deuteronolis. If Tharsis had finished growing before the ocean arrived, both should carry the same warping. They don't. Arabia carries almost all of the distortion, Deuteronolis only about a sixth, which means Tharsis was still erupting, still piling up mass, while standing water set in the lowlands right beside it. This wasn't a lake that sat unchanged for 1 billion years. This is roughly 700 million years of an ocean that kept expanding, shrinking, and reshaping itself around a planet still under construction. If the ocean's edges kept shifting because of a growing volcano, you'd still expect some trace of an ordinary beach. Wave-cut cliffs, sandbars, the kind of thing tides leave on every coastline on Earth. In a lot of places instead, there's just chaos. Terrain that doesn't look like gentle wave erosion. It looks like something hit it. Because something did. In 2019, A team led by French planetary scientist Francois Costar found a serious candidate for the source crater, Lomonosov, 75 miles across in what's now the Martian Arctic. Its rim is oddly wide and lopsided compared to similar craters nearby, exactly what you'd expect if the ground it struck wasn't bedrock, but a shallow sea that violently collapsed back into the fresh crater right after impact. Follow-up modeling of impacts this size, comparable to the asteroid that ended the dinosaurs on Earth, put the wave at around 500 meters tall in open water, still several hundred feet high on shore, racing over 900 miles inland and dropping car and house-sized boulders in the middle of nowhere. Mars couldn't just absorb one of these and move on. Statistically, an impact this size hit roughly every 30 million years, wiping out the evidence of the last one each time. That's the missing beach, solved. The beaches were there. They just kept getting demolished by nature's worst landscaping crew. For decades, everything in this story came from orbit. Photographs, radar, elevation maps. Nobody had actually put a rover's wheels on what was supposed to be an old seafloor and checked. Then, in May 2021, China's Yuan rover touched down in Utopia Planitia, chosen specifically because it sat along the interpreted ancient shoreline. Over the following year, Yuan drove nearly 2 miles south toward that old coastline, scanning the ground the entire way. What it found, published by researchers Bo Wu, Long Xiao, and colleagues through 2023 and 2024, reads like a field report from an actual beach. Rock, with fine, repetitive banding from sediment settling in still water, plus hydrated silica and sulfate salts, minerals that only form after real-time soaking in low-temperature water. Ground-penetrating radar even mapped a miniature shoreline profile underground, shallow near the old coast and deeper further out, exactly the layout you'd expect walking from a beach into the surf. And they pinned down the timing. A catastrophic flood filled this stretch of ocean around 3.68 billion years ago. It didn't stay open water for long. By roughly 3.42 billion years ago, it had frozen over for good. Call it 260 million years, start to finish. That's not, maybe there was water here once. That's a rover standing on an old seafloor, reading the minerals underneath its own wheels. So the ocean was real, reshaped by a growing volcano, periodically demolished by asteroids. Here's a question you probably haven't thought to ask. What did it actually taste like? Because it wasn't seawater, not the way you picture in it. Back in 1985, geochemist Stephen Kempe and Egon Degens proposed the soda ocean hypothesis. Oceans on young volcano carbon dioxide heavy planets don't start out salty like Earth's. They start alkaline, closer to dissolved baking soda than table salt. On early Mars, a thick CO2 atmosphere reacting with fresh volcanic rock dissolved enormous amounts of sodium, potassium, and carbonate into that basin, and Mars never developed the recycling systems that pull carbonate back out of seawater. So it just built up. Result, a pH somewhere between 9 and 11, between baking soda and water and ammonia glass cleaner. Closer to Lake Magadi in Kenya than anything on Earth's coastlands, and maybe not unlike the alkaline ocean hiding inside Enceladus, one of Saturn's moons, right now. Why does this matter? Water, that alkaline, changes the rules for how life can work, locking away metals like copper that nearly every living cell on Earth depends on, meaning any microbe here were making that rat rock collected in complete different toolkits, knowledge, Texas, and matter. Now here's where the story gets genuinely strange. On Earth, tides come from the moon, water bulging toward it and draining away, twice a day, driven by a satellite a quarter the size of our own planet. Mars's 2 moons, Phobos and Deimos, are basically useless for the job, small enough to tuck either one inside a mid-sized American city. Between them, they raise essentially no tide, which raises an odd question. NASA's Curiosity rover, exploring Gale Crater, an isolated lake basin nowhere near the Northern Ocean, has found rock layers with exactly the thick and thin banding you'd expect from water sloshing on a schedule. And Zerrom has spotted similar patterns back in the ocean basin itself. If Phobos and Deimos can't do this, what was? That question picked up real momentum in late 2025, when a team led by planetary scientist Ranjan Sarkar at Germany's Max Planck Institute found bands less than a millimeter thick in Gale Crater rock. matching tidal deposits found in estuaries on Earth, and calculated it would take a moon many times more massive than Phobos to produce a signal like that. Separately, astronomer Michael Efremsky at the U.S. Naval Observatory had already proposed, in 2024, that early Mars carried a much larger moon, a third the mass of our own, orbiting in sync while Mars's crest was still hot enough to bend under its pull. He named it Nerio, after the Roman war goddess who was Mars's wife. Put those two threads together, and you get a wild possibility. Ancient Mars had a real moon, big enough to raise tides and warp the young planet's shape before spiraling too close, crossing the Roche limit, and getting torn apart by its own gravity. Phobos and Deimos, in this picture, are just the leftover gravel. Worth being honest, this is a hypothesis, not settled fact. A moon that size, torn apart in orbit, should have left a trail of impact scars, and nobody's found one. And not every rhythmic pattern in sediment means tides, wind, seasons, and glacial melt can leave similar stripes. File this one as an open case, not a closed one. But it might be the single most fascinating unanswered question in Mars science right now. Whatever was pulling at that water, it eventually started to disappear. But disappear is doing a lot of work in that sentence. This ocean did not go quietly. As the basin filled with fine sediment from catastrophic floods, the layers at the bottom got buried deeper, soaked through, and squeezed under the growing weight piling on top. Eventually that pressure had nowhere left to go, and waterlogged mud fractured its way up through the crust, not lava, but liquefied sediment, bursting out across what now Chryse and Acidalia planetae as thousands of small, volcano-shaped mounds. Researchers have even linked some of these eruptions to the shock waves from those earlier megatast tsunamis, which would have compacted the wet sediment below and forced it to blow. The ocean was gone from the surface. It was still moving underground, erupting through the crust in slow motion, long after the last open water had frozen, and its last stand wasn't even down there, it was hiding under ice. For years, the assumption was that Martian glaciers, forming as the climate turned brutally cold around 3 billion years ago, were frozen solid straight to bedrock. No sliding, no melting, just slow, dry creep. Then, in 2015, researchers Coleman Gallagher and Matthew Baum found eskers in a mountain range called Flagramontes, long winding ridges of sand and gravel, the exact deposit left behind by meltwater running beneath a glacier. These dated to around 150 million years ago, practically yesterday, geologically. Deep inside the era Mars was supposed to be a frozen, bone-dry desert. Something down there was warm enough to melt ice from below, almost certainly leftover volcanic heat seeping up through a crack in the crust. Which means long after any ocean, long after the northern plains had frozen for good, there were still rivers running on Mars, just underneath the ice, out of sight, doing what water does, finding a way through. Which brings us to the biggest twist in this whole story, one that's only become clear in the last couple of years. For decades, the go-to explanation for the ocean's disappearance was simple. Mars lost its magnetic field, solar winds stripped its thick atmosphere, and sunlight broke water molecules apart at the surface, which leaked into space. One molecule at a time, over billions of years. That's still part of the story. It just isn't the whole story, not even close. NASA's InSight lander spent 4 years on the Martian surface, listening, not for anything alive, but for Mars quakes, tiny vibrations rippling through the crust. In August 2024, geophysicists Vashon Wright, Matthias Morsfeld, and Michael Monga published an analysis of that data in the Proceedings of the National Academy of Scientists, rewriting how scientists think about Mars as missing water. They ran the seismic readings, plus gravity measurements, against models of how sound travels through dry rock, ice, and waterlogged rock, to see which one matched what InSight recorded. Dry rock didn't fit. Ice didn't fit. What fit was rock somewhere between 7 and 12 miles down, so fractured its cracks are essentially saturated with liquid water. At that depth, heat from the planet's interior keeps things warm enough to stay liquid, even though the surface above is colder than almost anywhere on Earth. Run the numbers planet-wide, and you land on a layer 1 to 2 kilometers deep, a volume that matches, or beats, the highest estimates for the entire ancient ocean. Sit with that for a second. Mars might not have lost its ocean to space at all. Most of it may simply have sunk, drop by drop, into its own bedrock. and it could still be down there today. Not every scientist is convinced. Researchers, including Bruce Joukowsky and a separate team led by Richard Palin, argued that rocks sitting in scalding water for 3 billion years should have transformed into different minerals entirely, ones that wouldn't match the wet rock signal InSight picked up. It's a real ongoing argument, and it isn't settled. But even the most skeptical version agrees whatever's down there isn't simple dry stone, and liquid water is still the leading explanation. So how do scientists nail down the rest of it? One promising method borrows a trick from Earth's own deep past. Geochemists studying billion-year-old rock here use the rare earth element proxy, comparing light and heavy heat, versions of these elements trapped in ancient carbonate, to work out how acidic or alkaline the water was when the rock formed. If a future mission, maybe a Mars sample return spacecraft, gets its hands on real Martian carbonate, scientists could finally pin down the exact chemistry of that soda ocean and how thick an atmosphere Mars needed to keep it from freezing solid. Put the whole timeline together, and here's where we land. Mars didn't just have an ocean. For something like 700 million years, the better part of a billion, however you round it, it carried a genuine hydrosphere, an alkaline sea that grew and shrank as a volcano the size of a small continent rose beside it, that got torn open by asteroid strikes again and again, that may have been dragged into tides by a moon that no longer exists, and that, when it finally lost its grip on the surface, kept erupting through the crust as mud, and kept flowing beneath glaciers as meltwater, and, if this newest data holds up, never actually finished leaving at all. We didn't lose Mars's ocean, we just stopped knowing where to look for it. And somewhere down there, 7 to 12 miles beneath all that rust-colored dust, there might still be an answer waiting. If a story like this is the kind of thing that makes you look at the planet next door a little differently, that's exactly what we're here to do at Cosmos Coastline. Subscribe, and come dig through the rest of the solar system's best-kept secrets with us.